Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 6 and we will be today studying a brief idea about electrical conductions in solids. So the outline of the talk is we will be looking into the concept of conduction in solids and then look after the EK diagram. The EK diagram, as we have studied in our previous lecture, we will slightly go ahead in that case and try to collaborate or correlate that with the conduction band and valence band electron formation. We will look at the drift current and then we will also have a look at distribution of electron in the EK diagram. So what we will do is that with changing temperature, how does the electron occupy states in the EK diagram, that we will look, and from there we will try to extract the electron effective mass. And when we know what is the electron effective mass, we can actually look into the concept of hole, what is the meaning of hole, and then we will be looking into the energy band of metals, 3,5 semiconductor, which is gallium arsenide, GaAs, gallium arsenide, and then finally we will end this lecture with energy band structure for silicon, which is basically a semiconductor. So this is your metal which you have, right, and then you have silicon, which is a group 4 element, right, and this is basically a 3,5 element. Right. So this is compound semiconductor, this is elemental semiconductor which you see. So let's give you a brief account of how electrical conduction in solids takes place. Now if there is a covalent bonding in the semiconductor at T equals to 0, implying that there are no free electrons available, and therefore at T equals to 0, even if you apply some bias, you won't find any electron to be flowing. However, if you increase the temperature, or if the covalent bond between two atoms are broken by some means or other, or you add extra electron from outside, then if you apply an electric field in one direction, for example, if you are applying electric field in one direction, right, the electrons will start moving in the opposite direction because of its electrical charge is negative in nature, and therefore the force applied will be is equals to Q times E. Now Q will be minus E times E, and therefore if both are vector, so if you apply electric field in one direction, the force will be applicable to the other direction and the electron will be moving in the opposite direction. Now how does this formation takes place? That is shown by the right hand side conduction band and valence band diagram which you see here. If you see very closely, therefore, that there was an energy band gap which is given by Eg, and there's a valence band, there's a conduction band, and if I give an energy, then electron jumps from here, and actually electron jumps leaving a hole here which is basically a devoid of any negative charge, and negative charge appears in the top. Now total charge still remains the same, net charge is actually 0. Now let's also look into the fact that if we are plotting energy versus K diagram, E versus K diagram, then how does it influence the overall structure of the thing, right? Now if you plot E versus K diagram, then you very well know that top one is basically for electrons and this is for the holes. And so at T equals to 0, your bottom energy states are fully filled up. You see, all are put as blue here. Blue means that all the empty states here are filled with respect to each other, right? So all the empty states are filled here. So the occupancy probability is 1 in case of holes, and as you can see by the blue dotted curve here. And if you look at the top curve, in case of electrons, since there are no electrons available at T equals to 0, the occupancy probability is 0 and therefore you don't see that. But let us assume that we make our temperature slightly greater than 0, or let's make it 300 Kelvin or whatever, 250 Kelvin or so on and so forth. Then what will happen is electrons from the lower states here, some of them will start moving towards the higher states, and so electrons will occupy. So you see exactly the same number of electrons are generated as there are number of holes available here. So the electrical neutrality is still not broken, but you have a generation of large number of free electrons, right, and they go to the top side of the EK diagram, in the EK diagram. Now let's break apart from our understanding of wave function and EK diagram and explain to you what is a drift current. What is a drift current? Very simple and straightforward. In the presence of an electric field, if the charged particles are moving, then we define that current to be as a drift current. Why drift? Because it is drifting under the influence of a force, and that force is coming because of the electric field. So if you take this structure, let us suppose, whose width is B, whose height is C, and whose length is A, B, C if you see here, and there is a drift velocity Vd here, and you have applied a potential which is positive in nature, then finally you find a current which is given by this, right? N times Q times Bc times Vd. If you look carefully, B into C is nothing but this multiplied by this. So this is nothing but the cross sectional area, right, into A times Vd. This is your current. So this is N is the total number of charge carriers, Q is the Vd is the drift velocity, Q is the charge carrier, 1.6 into 10 to the power minus 19. Now if you want to find out current per unit area, then just take it down, and what comes out to be is NQ times Vd. So this is current density, areal current density. This is J or areal current density, and this is referred to as a, let me define to be as an areal current density, and it depends upon the drift velocity, number of charge carriers, and the Q value. So this is the basic drift function, but how does it move? Actually, I'll tell you how does it work it out. So if you now interestingly plot velocity of the charge particle, the drift velocity of the charge particle, and if you plot on the x-axis the electric field, and you go on increasing the electric field, and you try to check how does the velocity of the charge particles change, then it comes something like this. It comes like this for silicon, and then it becomes constant, which means that at low values of electric field, the drift velocity increases linearly with respect to electric field. At slightly intermediate values of electric field, Vd becomes a nonlinear function of electric field, and then it saturates beyond a particular point, which means that the Vd is constant, and the current therefore becomes constant, right? So the velocity will not go on increasing infinitely large in case of a semiconductor. And the reason being very simple, so you can appreciate this point. Now, when your electric field is relatively small and you are slightly increasing the electric field, the drift velocity goes on increasing. But as the drift velocity goes on increasing, per unit time, it starts to encounter a larger number of atoms of the semiconductor. And therefore, the scattering also increases. The rate of scattering also increases, right? And as a result, a time will come, velocity of the charge carriers moving forward, the force is exactly equals to the force which is being pushed back by the scattering forces. And when they become equal, the velocity becomes equal and there is no acceleration, right? This is also referred to as drift velocity versus electric field graph, right? And this gives you a fair idea that at some critical electric field, EC, let us suppose, the drift velocity becomes independent of the electric field and they becomes constant. So with this knowledge, let's look at the fact that how electron is basically distributed in E versus K diagram or EK diagram. Now, typically what is shown in the graph here is that for positive K values, you have lesser number of free electrons available, whereas for negative K value, you have larger number of electrons available. This is known as asymmetricity. In reality, you might have this under certain conditions, but in normal conditions, you will have equal probability of finding electron in the positive K as well as in the negative K, right? K is known as a wave number in a sense. Now, the drift velocity J is given by minus E times sum of the velocities from I equals to 1 to I equals to N. So, if you have N number of free electrons available, what you need to do is that you just sum the velocities of individual multiply that with Q, and with a negative sign gives you the value of your J, right? J, if you remember, the basic principle of J was here. Yes, you see NQ times Vd, NQ times Vd, right? So NQ times Vd, basically Vd sum is coming here, Q is coming here, and number is coming from I1 equals to N, that gives you the total current density J. Now, if you carefully in terms of the idea here, then you see that for each, if an electron has got this energy, it ideally can stay in two K values. One is this K1 here, and it is the negative value of K1 here, right? And this is true because E is proportional to K square. So obviously, for each energy value, you will have plus K and minus K as the value, which means that the energy of the electron will have the same value irrespective of the sign of the wave vector, right? So that's what I wanted to end up in for this slide at least. Now, if you look at from basic principles of Newtonian mechanics, and assuming that Newtonian mechanics work here, and if we define F total as a total force acting on the particle, F external is the total external force, and F internal is the total internal force, then F total, which will be the sum of X external, F means force, external force, plus internal force, must be equals to Ma. That's true, right? Nothing difficult to understand, that the total force will be equals to Ma. Ma is the mass of the particle and A is the acceleration. Now, this total force can be broken up into F external and F internal, right? And therefore, what we say is that if I assume that all the internal forces will balance out each other and this will be effectively equals to 0, my F external is given by therefore m into a, and let me add a term here, m star into a, where m star is the effective mass and a is the acceleration. Now I will try to explain to you what is the meaning of effective mass here, right? And then we will, from EK diagram also, we can predict the value of effective mass, which we will do in the next slide. But let's look what is the concept of effective mass. Effective mass is something like this, that if an electron is moving in the free space, right, and let us suppose it is stable in the free space and there is no electric field, then there is a rest mass associated with all the electrons, and that is given by m0, and this is referred to as a rest mass. So I have a rest mass of electron. But when the electron is under the influence of multiple forces in a lattice, then I cannot simply write down F equals to m into a. That acceleration which it is getting is not because of the rest mass of the electron, but because that the rest mass has now converted to effective mass, and the effective mass gives you an idea that under the influence of multiple forces, right, if a body is moving with certain acceleration, then we do a backtracking and say that F external by a is the effective mass of the electron. It is not m naught. M naught would have been the case had there been no influence external forces, single electron is moving in a electric field. Here if an electron is moving under external forces having large number of particles available, then you will have this F external as m star into a, and m star is defined as the effective mass. So the difference between effective mass and rest mass or other simple mass is, effective mass is when the particle is under the influence of multiple sources, and that you see in your semiconductor silicon lattice. Assume that I have a silicon lattice and electron is moving within the silicon lattice. So if you remember Kronig Penney model, there are multiple values of voltages at each and every point and their function of x distance. Now if I say that the average acceleration of the particle by virtue of all these forces is a, then we say the normalized value of the mass of the particle is m star in this case, such that if you multiply m star with a, I will get the F external. So this is the concept of effective electron mass. Let's now from the point of view of a EK diagram. Now I will again not solve it here for all practical purposes, but you see it is given by 1 by h cut square into d2e dk2 equals to 1 by m star. It will be 1 by m star, let us suppose. Now quite interestingly, it means that if your EK diagram is very very steep, then this value will be very very large, implying that my m star will be small. So if I have an EK diagram which is like this and I have an EK diagram which is something like this, so steeper it is, lower the value of effective mass will be. I leave as an exercise to you why is it like that. Mathematically it is explainable here, but with respect to my discussion in the previous slide, why does a steeper EK diagram gives me a lower m star, that you need to find out. Now if you look at the EK diagram at conduction band, the blue curve here, dotted blue curve here, is what actually it looks like, and what we assume for our practical purpose is we plot it like this black colored graph for the conduction band, and this is for the valence band. And interestingly, the approximation which we do internally is that for very high K, there is sort of energy saturation takes place, both for valence band and conduction band. We will not go into details of that. We are currently interested in this domain only, this part and this part, where K equals to approximately equals to 0. So as the K value increases, means velocity increases, there will be change in the value of the energy associated with the valence band and the conduction band electron and mass. Now concept of hole, if you remove an electron from a particular space, then what is left there is basically a hole. So basically electron moving from left to right implies that the hole is moving from right to left, right? So this is basically the concept of hole. So an absence of electron is basically a hole, right? And obviously, as you know, hole will therefore have a positive charge and electron does have a negative charge. Okay, so this was the concept of hole and then EK diagram which you see. Now let's take up a valence band and conduction band filled up states and empty states. Now if you look at the left hand side diagram, this is basically EK diagram of the valence states. So I told you that all the bottom states, valence states, are filled up, and therefore you see that all these are blue colored lines available here, except these few. These few are above this valence band, right? They are above the valence band. Since they are above the valence band, there is no requirement of filling, right? And that's the reason you see valence band with conventional filled states. What are the filled states? these are filled states and these are empty states. Okay. Now what happens is that there is a probability that the positive charges might appear on the unfilled states. Positive charges which you see, these are positive charges, these might appear in the unfilled states, right, in the original empty states available to us. So we have learned about EK diagram. From EK diagram, how to predict the effective mass we have understood, and we have also understood about the filled state and partially filled state. What is the meaning of effective mass and how is it different from rest mass? Let's come to the energy band of metals. We have already seen it. We quickly go through it. If you look very carefully, as I told you, that upper band and the lower band are sort of overlapping at this particular point, right? They are overlapping, and there the point of overlap is the place where you will find that all the electrons are free in nature. So even at t equals to 0, because of the overlapping of the states, you will find free electrons available, right? And that's primarily because you have a partially filled band available even at t equals to 0. So metal, therefore, even at room temperature or much below room temperature, starts to work as a conductor. You don't have to give an extra energy for a formation of electron, which you do primarily in case of semiconductor in order to form an electron. Here you don't have to worry about it because the states are already filled, conduction band states are already filled by electrons. Now this is just for the information, we won't be requiring this too much later on, but just for the completeness sake, let me show you the energy band diagram of gallium arsenide. And this you can see is very, very simple and straightforward. And you see, these are all direct band gap material where the minimum of the EK diagram here and here are just one below another. So let me explain to you what is direct band gap. So if I have this, right, and if I have this, they are directly same value. The minimum energy value falls on the same K. We define this to be as the direct band gap material. And if you have this and this is given like this, then you will have, this is known as the indirect band gap. So direct band gap and indirect band gap, please study yourself also to understand. Many a times one of them is used for optoelectronic purposes. So this is basically energy band structure diagram, and this is, as you can see, for silicon, the band gap is referred to as EG, which is conduction band. So silicon is basically an indirect band gap material. You see, the minimum is not lying on the same value of K, it has shifted. Now if you look at direct and indirect, then let's just draw once. This is a direct and this is indirect. Now this is basically energy versus K. So if you have electrons here, it can easily transit to this particular point. So an electron can actually recombine with a hole here, giving me an energy equals to Eg. But as it moves from high energy to low energy, its K value does not change, right? Its K value, wave number, still remains the same. Whereas for an indirect band gap material, if you come from this point to this point, not only the energy changes, its K value also changes, right? So I'm not explicitly stating in the class, but when you go back and have a look at your books, then please refer to what is known as conservation of momentum and energy, right? So one of them will have both conservation, another will have none of the conservation, right? So that's the energy band diagram of silicon. So each one of them has specific domain area of working. So what we did till now was we looked into EK diagram obviously, and then we tried to predict what is a direct and indirect band gap material and how does it influence the overall structure of the system. So we looked into direct band gap material and we looked into indirect band gap material. And in direct band gap material, no change in K. So momentum is conserved in this case. And in this case, direct, there is change in K, right? That is one thing which one should know. The second thing which we learned was that, obviously, this is a well-known fact. For metals, you have overlap of CB and conduction band and valence band, and therefore there is a large electron density at T equals to 0 Kelvin. The third thing which we learned was that as the temperature increases, the EK diagram, the lower EK diagram gets traditionally empty and the upper EK diagram gets traditionally filled up. Then these three basic things we have seen, and then indirect and direct band gap, and then we concept of hole also we looked into the matter, and then the concept of effective mass of electron, right? And it depends therefore on the curvature of the EK diagram. And we learned that if you have an Ek diagram curvature, then if it is more steeper, then higher value becomes d2e dk2 is much higher, and therefore v 1 by h cut square into d2e dk2 equals to 1 by m star, let us suppose. Then this m star, so higher the value of d2e dk2 is much higher, then m star is much lower in order to entertain with the value, which means more steeper is the Ek diagram, higher the value of your m star or the effective mass of the electron, right. So this we have learned from this recapitulation from this course. When we meet next time, we will go into the foundation of solid state theory, and then we will look into the density of states and the probability function, right. So that we will do in the next lecture as we move along. Thank you for your patient hearing.